It's gotta be the parking or something.
Yeah, some of them,
It
two of
has
them are
nothing-
closed.
It has nothing to do with the results of the exam, nothing.
Yeah, because if anything, it should inspire you to be here more, right?
Good thing. It's parking.
This parking. So as a reminder, because a couple people did ask, exam number 3 will be on our prescribed date for the final, whatever that is. That's our exam 3, right? So that's Friday, the December 16th. Oh, yes.
What do you say? What do you say?
Say again?
December 16th.
No,
The
no.
final?
Just like
final?
Midterm 3 final.
chapter, exams 1 and 2 with the material from the prior to that point. Other questions? Yeah.
Is it possible to kind of curve the test where like the 20s becomes the C's, the 30s becomes the B's, the 40s becomes the A?
I will be, I constantly analyze
Uh-huh.
the class status, and sometimes, in lieu of doing an actual curve, sometimes I forgive a question or something like that, if that's warranted. So I look at data like that, and then I determine if there's something I can do to help, that I should be doing to help the class at large. If it's this group here who's doing really well and everybody else isn't, then that's another thing I like to recognize. Those students actually here in class is kind of a big deal. I don't give points for being in class, but you're here to get tips and materials and try to help you understand it, and it's, you're putting in your time, whereas some of these other people are not. So I understand there's other exams going on and study groups and stuff, so there is that we're competing with as well, but
I said right now, where do we stand?
right now where we stand, yes, I'm looking at the data, and I will very likely be doing some adjustments.
Yay.
Yes. Yeah, it's, yeah, and part of it too, well, no, I'll just leave it at that. I'm looking at the data, I'm gonna be doing some adjustments as I see.
I'll take that.
I'll go with that.
Other questions?
How's the grading for assignment 3 or 2?
Assignment 2. Yeah, it's just started.
Oh.
When are we
Right,
gonna
so-
start assignment 3?
I am gonna post it this weekend. I was hoping to get it posted before this lecture, but I didn't. So
Are we gonna
I'm-
get till the end of the semester too?
Yes.
Okay.
You'll
Also-
get to the end of the semester, turn in the assignment 3. It's gonna, well, I won't say anything more about that, but I'm gonna post it this weekend. I wanna get it earlier rather than later.
Yeah.
Though you can be looking at it this weekend, and then Monday we can come back and clarify what you read. Yeah.
Is the final based on the whole material throughout the semester, or just from now until the end of the semester?
No, it's material we covered from exam number 2 to that point. It's not comprehensive. Just my syllabus. Exams are not comprehensive, they're just for those chapters between exams.
So in this case, it's gonna be from 4 till whatever.
Yeah,
45 first.
and what I'll be, the study guide will be a little bit more interesting on this one because we're gonna go a little faster on some topics, and so I'll give you some focused points for the chapters I'm wanting you to test, really be studying what's going to test.
Is it possible? Are you giving us practice problems? Like, you remember how like the first you used to give us like a little problems to
Yeah.
work through? I kind of like that just because like I kept myself on track, like making sure like I did those before the next class meeting.
Mhm.
Can you start doing that or no?
There's some in here,
Okay,
yeah.
just I like that, it helps me.
Matter of fact, we passed over one last lecture.
I kind of did that one already. The
Oh,
one
good.
that yeah.
Oh, good, yeah, because that's the type of thing, I'm glad for,
Like a-
thank you for the feedback. Hopefully that's what everybody else is thinking too, because, oh, good.
Yeah, because when we wait till the end, it's just a lot to work through.
Okay, that's a good point. I will,
Just like 1 or 2 problems for like per lecture kind of helps review what we covered.
okay, I like that. I
Okay.
will do more of that. Other questions or feedback? Yes.
You said the exam is on the 16th, I had the 14th written for some reason.
It's Friday, whatever date the
Friday.
Friday is. So whatever, we have last lecture, and then a couple days later is Friday, and that's the date of the exam, and it starts at 1800.
Friday at finals week? Oh,
Yeah.
okay.
Just as posted online at the SDSU site, right? Go to the class schedule, and it says exam, final schedule, right? Click on that, you'll see Monday, Wednesdays, 1700 and later, Friday, some day. And that's ours. Other questions or suggestions? So what question would you like to see?
Yeah, mine is.
Yeah, sir.
All right, so let's go ahead and pick up from where we left off then. Of course, questions are welcome at any point in time. So we stopped here and then we started to talk about an example, another example. Okay, because we talked, remember we were up to this point talking about state
This one.
diagrams, right? And there were the two different approaches, Moore's and Mealy's. Sound familiar? Okay. So we're taking a look at some definitions here so that we can now maybe work ourselves into an example to see how we might use state transition diagrams to help us analyze these problems and come up with some combinational circuits to solve them, okay? So in this particular example here, what we're doing is we're looking for patterns. Now, we were calling them sequence recognizers. Officially, they are sequence recognizers, but it's about patterns, detecting patterns, okay? So in this particular example, we're going to look at something that can recognize that pattern of 1101. It's a really interesting pattern because, for one thing, it has a sub-pattern to it, 11. Okay, which you'll find frequently in binary numbers. You'll see 11s popping up all over the place. And we're looking for a little longer string where we have the 1101. So this is a kind of an interesting example because we have both of these things in play. So it's some patterns as well as full patterns. Okay? So what that means, in order for us to be able to recognize the pattern 1101, somebody's trying to kill me here. But I do know it's none of you, so that's all right. So in order for us to recognize some sequence like 1101, one of the things that implies is that we have the ability, of course, to recognize a digit and that it is in our alphabet, 0 and 1, but it also implies something else, right? And that is, once I've detected this, I need to remember that I detected this, so when I come here, I can now look and see if I detect this followed by this as a pattern that I expect to see, right? So there is this notion of memory as we're working through our recognition system, okay? We're going to have memory because if I'm looking at a 4-bit string and I'm trying to match it to 1101 and I come up with a 1001, right? I recognize this is great. I come to here. If it's not a 1, there is no sense in reading the last 2 bits, is there? Because it's not gonna match. You are done at that point, right? So there is this notion implied here of memory in order for us to implement some system that can recognize the sequence of bits in specific patterns, okay? So looking at this, of course, we need to do it for the full string in order to recognize it. The other thing that might not jump out at you until you start looking at a bunch of different patterns is that for one, say 32-bit word, if you're working with 32-bit strings, okay, you might actually have multiple instances of this in that string. In which case, you ask the question, do I recognize 1, the first one? Do I recognize 1, the last one? Or do I recognize all of them? Right? And those are your 3 choices. Obviously, you don't recognize 1, you don't recognize. So that one's kind of out, but the others are true. So in this example here, it's kind of interesting because we do have this string here. In this case, we have a 7-bit pattern, and we have 2 repetitions, if you will, of the pattern 1101. We have 1101, you see in the red, but if you ignore that, you look at the ending part, you say, oh, I've got a 1101 down here as well. Okay, so I have 7 bits, 4-bit pattern. That means I am sharing at least 1 bit, right? If I'm going to recognize that string 1101 twice, I have at least 1 bit that I am sharing. And so in this case here, that is true. The 1101, this one here, was part of that first 4, but it was also the first bit in the 1101 for the second. Okay? So typically, we like to recognize both of those sequences. We're not necessarily going to throw out the second one just because we recognize the first one. Okay? We want every instance recognized. But we don't care if some bits are used more than once. All right, so that's the problem. That's the example. But in order for us to start tackling this thing, one of the approaches, because you were reading this whole, remember we kind of went over fairly quickly this whole design procedure, but you've done the reading. Okay, so one of the things we're doing is we're formulating the problem, which we just did. But now we need to start doing our analysis of the problem. And we're going to use state diagrams to help us understand how to approach developing a solution to implement one of these sequence recognizers. Okay, so we're going to use a state transition diagram to do that. So when we start defining our states, we always have an initial state, right? One of our early on design definitions is I have to have that initial state. That initial state typically has to deal with scanning the first bit. Kind of makes sense, but again, it may be obvious, but you still have to do it. If you don't do it, then you do it, your sequence recognizer is not going to work. So in this particular case, we're going to read a bit, and we're only going to start recognizing something if that first bit is a 1, because the first bit in our 1101 is a 1, right? If the first bit is a 0, we are done. Well, not completely done because I've got more bits to read, right? So the second bit might be my pattern of 1101. All right, so I have to have an initial state. The initial state has to be able to recognize that it's a 1 or a 0. If it's a 0, it wants to reset itself and start a new scan with the remaining bits. If it's a 1, then it wants to transition into another state that looks to see if it is immediately followed by a 1, right? Because we have 1, 1, 0, 1. Okay, so that's how we want to approach this thing. Initial state, scan the input, is it a 1 or a 0? If it's a 1, then I want to create my next state to process it. If it's a 1, or to go back to the first state if it's a 0. All right, so I have my second one. Right, so I have A, it was a 1. Right, so I transitioned to B, and it was a 1. Okay, then I need my third state. And the third state says, hey, the third one needs to be a 0. So here's where the history is being implemented. Now you can get a pretty good picture of that history, right? If I start with A, and I can only transition to B if it's a 1, and now I'm in B, and I can only transition to C if it's a 0, also a 1. That's how I remember that I had a 1 followed by a 1. Okay, so now I can build that third state, which says, oh, it needs to be a 0 before I can transition to D. Okay, and so we can see the 1, 1 now, and now we recognize a 0, and that means the D state needs to be a 1 in order for us to recognize this string. So we just built our transition diagram this way, where we say I want this, a 1 transitions me to B, a 1, another 1 that transitions us to C, I want a 0 that transitions to C, and then another 1 transitions to D. I recognize it as a substring, and off we go. Okay? So that's what we're doing with these state transition diagrams. Yes?
Does the 1, it says 1, 1, does it that 1 to the, right? Is that stating that there's one recognition of that pattern? Or what is that one?
Oh,
Because you
you
know how
mean-
the rest have 0, 0, and that one has 1, 1?
This one here, you mean?
Yeah.
So at this point, this is the end of our string that we're trying to recognize, right?
Uh-huh.
So in this case here, if I have a 0, I'm done. If I have a 1, then I can recognize not only the pattern, but I can also exit the system. Now, another thing to ask yourselves, let's go back here to state A. While I am in state A, have I recognized the first 1? No. Right? I haven't actually recognized anything in state A. I am reading the first bit, right? Once I've read the first bit, then I have an event. That bit is 1 or 0. If it's a 1, I transition to B. 0, I'm incomplete. Okay? Or if it's a bit 0, I'm out of this thing altogether, right? I exit. And same thing repeats with B, C, and D. So that's another way of looking at this is that while you're in the state, you haven't read that bit yet. Just completed the prior action. That's how you got into this state. Okay? All right, so the final one obviously recognizes a string 1101, okay? But what's really interesting here is that if the next bit were a 0, then we know we don't have any sort of immediate repetition of this pattern, right? Because I can only have an immediate repetition of this pattern if this bit were a 1, right? Because the bit would have to be 1 to be this one or this one. Well, in this case here, if I had a 1 here, I'd immediately jump into this state, right? If my pattern were 1, 0, 1, 1, it'd be different, right? If it followed up as a 1, I would have to transition to state A. You see that? Anybody not see that? Okay. Because this has a repeating 1 pattern, I get to reuse that first one. So if my string is followed by a 1, then I would transition back into state B, not state A, because I already have
A 1.
a 1, the first one, and I just recognize the second one. Okay, so this just follows up with the other cases, but it sounds like you've got it. All right, so another way to say it is looking at it from the immediate approach, which says, oh, let's just focus on the arcs, right? Because the arcs are where I'm recognizing the bits. I know I'm an A. Okay, now that I'm an A, I'm going to forget about states, sort of, kind of. I'm going to recognize a bit from A. 0 arc means, what does 0 arc mean?
Like if you were at state A and you process to 0, where you're supposed to go, it's not clear. That's missing.
Not quite.
Yeah, it would go to a null state.
The goal null state, right?
Right, but it's not there in the picture. It's missing.
It is missing because a complete state transition diagram would show the error states. This is not. We're only showing that part that recognizes it because we want to build a recognizer with the assumption, and I hate that because I never assume anything when I'm doing design, but the assumption that if I don't have something that can recognize the input that I have, then I exit. Which I don't really care for, but that is how your author chose to design this, because that's how really was focused on the problem definition, right? Worrying about how do I transition transition states rather, as opposed to the overall picture. All right, so we can add those. We certainly could add those, right? If I were an A and I recognized a 0, what would I do? When you started to say it.
Go to null state.
Go to null state, right? Which I would do by,
Making a new state, drawing R2.
yeah, I'd make a new state, or I would exit this system, draw an arc coming out of it. Either way.
Is an arc like an arrow?
Yeah, these arcs
Okay.
are the arrows with the mnemonic, right? Those are our arcs. With a C, not with a K. Right?
Oh.
So yeah, that's exactly right. The arcs that are missing are error conditions, are exit states. So I'll create an exit state, and from each of these states, I should draw an arc, ARC, showing how to get to an error state or exit state. Another way you can do it, however, is simply to reset your state machine. Instead of going to an error state, you simply go back to your initial state, A. Because if you're not done reading bits, the fact that you encountered this bit that was good, this bit that wasn't so good, you had some other bits later on, right? You don't really want to exit the system at that point. You really want to go back to state A. Okay, so I would go from state A to state B. This would take me back to state A, right? I'd read this, I'd stay in state A, which is what you see up there in this diagram with the blue arc that says 0, 0 on it, right? It's going back, transitioning back to itself. I get this one here, right? Ooh, I've got a 1, I'm in state A, so I want to transition to state B, which is recognizing a 1. I don't have a 1. So 0, 0 takes me back to state A. I come here, I have a 1, so I'll transition from state A to state B. I come here, I have a 1, ooh, I'm getting further. I transition from state B to state C. State C says I will need a 0, I have a 0, so I transition from C to D. Here, I have a 1, so I transition back to
A? No, wait. Yeah, A.
no.
B.
No.
Because you have a...
C.
What?
No,
D.
no,
No, wait, from D? You're going back to...
no.
You're going to C.
Hold on.
That's because I was listening. I was checking to see if you were listening. Because we're
Yeah, this is
excited
A.
because we recognize something, right? I'm in state. At this point, I am
C.
in state
C.
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 You didn't say C.
Oh,
Yeah.
yeah, because it doesn't move
You haven't
initially,
transitioned.
that's why. So
Right.
they check the
Yeah.
second one, they check the first one, right after.
Right, exactly. Here's where I'm checking the next bit. Right? Here's where I'm checking the next bit. There's where I'm checking the next bit. So here, great, I've recognized this. What's my next bit? 0. So that next bit then would cause me to transition to state A. But I have recognized the string. So I've classified this as a recognition. I checked the next bit, it was a 0, so I go back to state A. I read it, it's a 0. Next bit is a 0, so I transition to state A. Next bit is a 1, so I transition to state B. Next one is a 0, so I transition to state
A.
A. Hopefully you listen carefully.
Transition and what else?
Say again?
It was transition and what else?
Transition and states, right? I
And
have
states, okay.
states and I have transitions. The important thing, hopefully you were listening, is that I am, what's not really shown here, right, is I am in state A, right? And I read this bit. This bit's a 1, so I transition into state B. So now I'm in state B. I read the next bit, it's a 0, so I transition into state A. Okay? So I'm in a state, I'm reading the next bit, and I only transition when that bit meets the criteria for the next state. If the next state is C, I go to C. If the next state is A, I go to A. And if I constructed this correctly, like what I did here, at any point of recognition, I can go back to state A, which resets everything. I do not recognize the substring unless I had transitioned from state D. And then I have recognized the substring, but I continue because I've got another bit. That's important because in addition to your initial state, you also need to have a final state. And we didn't talk about that here. Your author kind of left you hanging a little bit. But if you're in state A and you have no more bits, then you do need to have an exit state. Okay? So that's the thing that's really confusing, I think, a little bit about the author's reading, your readings from the author's text, is that that part is left out, but that's an important part. Because the whole idea of recognizing this string, or substring to be more accurate, is you're classifying this, and so you're recognizing that, you're putting it somewhere, but also you're recognizing that you are at the end of this string when you're in this state, and there's no more bits to be read. Okay? So, having walked through that now, I think we all have a pretty good handle on it. We can actually create our state table, right? And this one's going to be pretty straightforward because we have 4 states because we're ignoring that end state thing, right? So we have 4 states, and we have 1, 2, 3, 4, 5, 6, 7, 8 different ways of transitioning. All right, so we're going to use, what's this kind of table called? We introduced a name for this last lecture.
State diagram.
It's a specific kind.
Or state table.
Yes, it is a state table, but it's a specific kind of state table. We had a name for this. Notice how we have two variables, 2 outcomes actually. We have 2 outcomes in one column of our table. We had a name for this, remember? The numbers aren't. This was our abbreviated state table, wasn't it? Okay, so our abbreviated state table, we convinced ourselves last lecture, even though we were distracted about what the exam score might have been, we were kind of interested in this, right? Because we made the table smaller instead of having a whole lot more rows than it could have had. We combined some elements that had what in common? These 2 elements had something in common. What were they? And I say these 2 specifically because we combined them in the same cell. So what do they have in common?
For both states.
What's that?
For both states.
I was gonna say that.
They have at the same time.
Say it again?
At the same time, T1 or T2.
They're all going to be at the same time. Right.
That's
So
like
they're all
this.
going to, all of these are going to be at the same time.
They're both coming from state A.
In this diagram, yes. This table rather, yes. These are all coming from A.
Or like, yeah.
There was a more generic definition I was looking for, and that is they're going to both have the same value, right? So coming from state 8, if x is 0 or x is 1 in the next state, I'm going to have the same values. Okay, so that's what enables us to create these abbreviated state tables. I could draw the full one out, and then through an analysis, looking at the patterns, I could see, hey, if I'm in state A and x is 0, I'm always going to go to A, and my output is always going to be 0. And that means if it's B, its output is always 0. You have this commonality at every single occurrence. You could then combine these 2 pieces of information together in a single cell because it's just going to repeat when you do it uniquely for this pair and then again for this pair. That's what enabled us to create this abbreviated state table. And the abbreviated state tables are really nice to do because they're a lot easier to analyze, right? So go back, if you're not really sure about that, go back and look at the discussion and the readings on abbreviated state tables and make sure you understand that aspect of it, because we're going to use it over and over again. Okay, and there's some properties that we can predict patterns of repetition. Okay, there's ways to do that. So in this particular example here, we're saying that, hey, anytime I'm in state A, if my next state and my output are zeros, they're going to be the same. Likewise, ones, they're going to be the same. Okay? So now I can go ahead for every one of these states, if I'm in A and x is 0 or 1, I can tell you what its output is going to be, right? So we can fill in the rest of this table, right? For example, state B. If I'm in state B, right, x is either going to be 0 or 1. What if x is 0? Go to A, right? So this would be A. Its output was 0, right? What if it was 1?
Go B.
It goes to C, because its output was 1. So we're just simply filling it in. Now, your diagram's already told you the values, right? You've got your outputs, 0, 1, okay, are your two outputs for A. For B, your two outputs are 1, 0. For C, your two. My output from B is a 1 or a 0. Right? 1 is going to take me to C. 0 is going to take me back to A.
Those are the inputs and then
My outputs from A, that red line, that red arc, if my output is a 1, then I transition from A to B.
isn't it input slash output? So like, if you're coming from A, you're always outputting 0, and your input could be 0 or 1.
My output from A is 1. My input to B is 0. Okay, so in every one of these, you notice you just have two outputs because you're either going to recognize a 1 or a 0. You may have, actually this one I think we do, yeah. You may have more inputs than 2, right? You're only going to have 2 outputs because you're going to have exactly a 1 or a 0. And you need to go to a deterministic location or a deterministic state. It's actually a very good point if you haven't realized this, is that if I had if I had 1, if I recognize 1, and when I'm in state A, I need to go into one specific state. It cannot be ambiguous. It cannot say, go to state A or go to state B. Because you have no way to discern how to go from state A or to state B if you can go to either state if you had recognized a 1. That make sense? Yes?
Just to clarify, like in the table,
Yeah.
if you're in state A, and then the next state column, if x equals 1, and you go to B,
Yeah.
the output says 0, right?
So x is my output, right? So that means I've input into B is 0, which is what that column is. X is my output. Is that how you write it?
That's not how I read it.
Okay, if I'm confusing you, stick with your author's definition. Okay, we're saying the same thing, we're just saying it in different contexts. So yes, the output would be 0 according to his definition. That's perfectly fine. I'm looking at it from a state transition diagram, not a Mealy state diagram, my fault. Okay, from a Mealy perspective, yes, output is 0. Important point though, you do recognize that in order for us to have a deterministic model, there is only one state you can transition into. Right? Okay. So this shows you the sequence that you can go to recognize a string. Recognizing that in the Mealy model, the only time you have an output of 1 is when you recognize the string of 1101, right? All other interim outputs need to be 0 in order for you to proceed. So if I'm in state A, then my next state needs to be B. If I'm in B, it needs to be C. C, this is interesting. I need to recognize a 0, so it's going to be D. Then D, I want to go to A. Right? I recognize the string, and then I return back to the gate. All right, so that was the Mealy model. Now for the Moore model, okay, we need to modify this a little bit because in the Moore model, remember, we're also worried about the interim values. So we are going to introduce the E-state, which allows us to be able to capture that I recognize the substring moment, if you will, which the Mealy model just had built into their definitions of outputs and the way that they processed it. Okay, so what we're going to do now is we're only, and this is more I jumped ahead of this one. This is more of the purest state transition diagram modeling techniques. Here is where arcs are built upon its recognized outputs. So now in the Moore model, we're going to do my previous description, which was, okay, if I'm in state A and I read the next bit and it is a 1, my arc recognizes it as a 1, I transition into state B. If I'm in state B, and then I read a 0, okay, that's not the next bit, I then transition back into state A, or if it's a 1, I then output from state B, transition into state C, having recognized the 1, and then I would just continue the string. Now notice that when I do get to the end here, and I've recognized the 1101, all right, if the next bit was a 0, I transition to state A because I need to begin all over again. If, however, the next bit is a 1, I go into my E state. Okay? The idea with the E state is that, oh, I've recognized this value, and depending upon whether the next bit is a 1, that's saying I had a 1101 followed by another 1, then I can transition into state C and look for a following 0. Otherwise, I then transition into state A and begin the sequence all over again. Okay, so this one's a little bit more complicated because I have introduced a 5th state and because I now have more arcs. Right?
Seems easier though.
It's straight, in some sense, it's more straight ahead because every arc has a very singular meaning to it instead of, I focused on the output was whether or not I'm continuing or not, right? So in addition to what was the value. So you had the value you recognized and do I get to continue? Was built into Mealy, whereas Moore says, I'm just going to take every state transition for what it is, in which case I have to build this event state right here. Okay, so its state diagram would look just a little bit different. Okay, because if you remember in the Mealy model, we had combined output of x equal 1 and x equals 0 into a column, but we also had the pair of outputs because every arc had a pair of values to it, right? Recognized and value. So in the Moore model, now all I care about is whether or not I get to continue, right? So from A, if I had a value of 1, I continue. From B, if I had a value of 1, continue, and so on. And if I finally get to the ends, if I finally get down to state E, which is the only place I can recognize that substring, then I can go ahead and declare that the substring was recognized, And I can then transition based upon the next bit into either state A or C, which is declared right there. Okay? All right, so in this example here, the question you come up with, first off, when you're looking at state tables, and something I failed to do when I first looked at my first state table, was looking at the state table, you now should be able to recognize if this is a Moore model or a Mealy model. And the key thing that you use to determine whether it's a Moore or a Mealy is your output column. Just like we were talking about, right? Because the output column in this example here, where it could have 0 or 1, tells me this is a Mealy model, right?
Yeah.
Okay. In the Moore model, you would have just output. Right? So now comes the next step. Okay, I've got this state diagram, I've got this state table. At some point, we need to start designing hardware. Right? Okay, so one of the things we can do is we can look at each of these different codes and say, you know, which ones are essential, right? Excuse me. Or we can just say, let's go ahead and implement them all and then maybe optimize later. That's really the two things you can do when you're looking at these tables. Either try to do some optimization now, or just go ahead and build this thing out and then do optimization. Okay, so for now, what we're going to do is just go ahead and build circuits for every one of our states. Okay, so to do that in this example here, what we're saying is that, given some state, now notice I'm getting away from my A's and B's, right? Because I need to worry about numbering my different states that I had, A, B, C, D. Okay. They were all A, B, C, D. I have my 4 states, which take exactly 2 bits to implement, 0, 1, 2, 3, for my A, B, C, D, right? So I just code them up that way, A, B, C, D as 1, 0, 1, 2, 3. Okay, and then from there, I'm just simply saying, oh, I can go into state 0 or state 1, state 0 or 2, state 3 or 2, state 0 or 1. And in each of those cases, I know what my output values are. So I'm simply just doing a translation, right? So I can get from characters, which I can't implement circuits for, to bits, which I can implement circuits for. Okay? So that was step 1. All right, so another thing that we can do is go, it was the same thing. Another thing I can do is say, okay, now that I've encoded all my bits, I still am worried about those cases where I may not care. Yes?
It looks like you switched 2 and 3.
Oh, yes, I did that because I was jumping ahead to this next slide. So he got that, we flipped these. I flipped those because what I started to say was that once I recognize that I need to implement the 4 states, and if I'm still concerned with optimization, which we're always concerned with optimization, then from our previous discussions, we know that we need to go to the K-maps, right? And the K-maps are, in this particular case, are going to be very similar to implement than what we had seen in the previous one. And as you recall, in our K-maps, let's go ahead and build the 4, right? We would go 1, 2,
0.
thank you. We go 0, 1,
3,
2, 3,
4,
4,
5,
5,
7,
6,
6,
7,
8,
8,
9,
9,
10,
10, 11,
12,
12, 13, 14, 15, right? So in this case here, which is simpler because it's only a 2 by 3 instead of 4 by 4, we need to do the same type of thing. So instead of simply labeling it 0, 1, 2, 3 like this and the rest of our columns that way, we go ahead and reorder them like we did prepping for our K-maps, so that exactly we go 0, 1, 2, 3, and we go 0, 1, 2, 3, 4, 5. Okay? So that way we can go ahead and draw these different, what's eventually going to be gates, right? So we have y1 and y1, y2, and x naught for d1, u2, dz. And then we just simply fill in for d1, d2, and x. Okay? Once we've translated those bits over, then we can start looking for the patterns, just like we did in our other K-maps, right? Always wanting to go with the largest. Now, in these small tables like this, these 2 by 4 tables, right? We're not going to we're probably not going to find a grouping of 4, although it's still possible. So you still want to look for your groupings of 4. If you find it, great. But in most cases, you're going to have 2s and 1s, and that's what we show here. So once you've identified those, then for D1, you can then start deriving the functions. Okay. Once you've defined those functions, then you can go ahead and implement them. Right? Make sense? So we're just using those tools we had before, but now we're just applying them specifically to these D-latch flip-flops. Getting from state models to state tables to our K-maps to implement D flip-flops using those equations. Right? So here's another example. Okay, same type of thing where we're going to assume D flip-flops. And we want to derive our K-maps. Okay, so here's what this example looks like, where we have case of y1s, x naught, y2. Pretty straightforward, but the reason why this one was interesting is because when you look over D2, just like I was mentioning before, we do have the possibility of some cases where we have a pattern, a 4-bit pattern that we can just go ahead and optimize that way, which is really cool because in the case of the D2 D-latch, it's always going to be X, right? It's X, it's set. Otherwise, I don't have to implement any other logic, and it becomes a lot more easier to implement. Likewise, my Z case is also pretty straightforward. There's only this one condition. When I have X, Y1, but not Y2, that's the only time I recognize it. So the only one that's a little more complex is my first D-latch. All right, so any questions before we move on? No? Okay. All right, so D flip-flops. Okay, in your libraries, we have these D flip-flops. You can implement them, pretty straightforward manners. I mean, if you look at just this lower part here, we had just X clock and reset. It's just standard standalone D latch flip-flop with a Y2 out. Okay, but creating other logic circuits that are either using feedbacks or some other combination of AND gates, NAND gates, OR gates, NOR gates. You can create, of course, additional logic like we're talking about here, which gives it a little bit more complexity, requires a little bit more hardware, but enables us to implement these functions. Okay? So what we're looking to do is to say, how can I create hardware to implement any of these functions? Okay, so I have what? X coming in. And I have Y1 and I have Y2. So going back and looking at this example here where we started with this pretty simple one, D2 is always X, right? So in this case there, D2 is always X. You can see it coming out right there as Y2 coming into this. Z, however, X, Y1, not Y2, we can implement this way here. We say Z is Y1, so we'll take the output of Y1, not Y2, and then X is also pretty straightforward to implement. Okay, so we can quickly develop logic for the Z output and for Y2. Those were pretty straightforward because we had some pretty nice optimizations in our K-maps, right? So they're pretty easy to implement with circuits like this. The more complex one, though, as we were just talking about, was the Y1, because Y1, in this case it's going to be our D1, needs to have this pair. So let's write it over here. Right? D1 is Y1 and Y2, or X and Y2. Okay, so right here we know we have an OR gate with one of these two terms going into, with both of these two terms going into it, right? X is our only input into this system. So we have a direct X going straight into this AND gate. That's how we're going to implement these, right? These are going to be AND gates. If I can draw an AND gate, we might be able to progress back to this line. Right? So this is an AND gate, which looks something like that, where we have X coming in, and we also have Y2 coming in. Y2 is going to be coming from that other latch, D-latch flip-flop, right? This one here is an AND gate with Y1 coming in and Y2 coming in. Oh, so I've got two feedback loops coming into this AND gate, right? One from the D-latch Y1 itself, as well as the other D-latch. So that's what we probably should see over here. And in fact, we do. Taking Y2 out over here, coming up to the top AND gate, as well as the output of Y1 is the other input to the AND gate, just like we drew over there. This AND gate down here, we have X coming in, and we have Y2 coming in, just like we said there. So we have that or that feeds into the D latch to generate the Y1 out. So that's how you go from here to actual hardware components. Make sense? So now you've done the whole thing. We started off with the problem statement. How can I recognize a sequence? 1, 1, 0, 1. Built your state model. Decided whether you wanted to use Mealy or more. And then you derived your state table. From your state table, you then constructed your K-maps. From the K-maps, you derived your algorithms, equations. And from your equations, you're able to then define your components in their interrelationships. Now you can design a circuit. Feels good, right? What are all the doubtful faces about? Sure you can. It's just doing different combinations now at this point. You've seen a couple examples. You walked all the way from, like I said, the problem statement to circuits. You can do this. Of course, remember that we have clocks and resets, so we'll be sure to add those to these. And the other thing that we take into consideration is, well, cost of chips. Okay, so is it more expensive to use AND gates than NAND gates, or less expensive? You know, what are the costs of your different packages? And so you sometimes will optimize by going away from, once you've constructed like the basic logic, 2 ANDs feeding an OR, you find out that it's actually cheaper because you can buy a single chip package with 4 NAND gates on it, instead of buying 2 packages, one with 4 AND gates on it and another package with 4 OR gates on it, and you only use 2 ANDs and 1 OR. Okay, so that's what this is talking about here, is that saying, ooh, I've got 2 ANDs and an OR, but I can buy these packages where I have 4 of one on one chip and 4 of one on another chip. That's 2 chips, but I can buy a whole package of 4 NANDs and I have a single chip. Okay, and you go through the logic and you recognize, wait a minute, that's saying the same thing as this is saying, then you know you can optimize your solution that way. Okay? Just as a hint, I'm less interested in chip optimization discussions in this class at this level. I'm more interested in how do we get to this slide. Okay, how do we get to this solution, more importantly. I'm much more interested in how we got to this solution than taking it this next step of optimizing it for chip components themselves and cost. Okay. Yes, it's a big deal. Yes, it'll be in your study guides, but you can take it for what it may be. I'm much more interested in getting here than I am here. Okay? Questions? Yes?
Is a Moore model different than an automata?
These are all automatas. So here's the deal with, so the question is a Moore model the same or different than an automata? What an automata is a machine, a stateful machine that can unambiguously define an outcome. Which is why I spent several seconds stressing and emphasizing unambiguous state transitions. Great question. Those of you who are going to go on to graduate studies, it will be a big deal when you start worrying about finite automata and discrete state machines. It's a big deal. Other questions? Okay, well, we've just finished this chapter, and while I could go ahead and start the next one, I think I'll forego that by turning you loose. Those of you who haven't picked up your exams yet,